and self. And I'm not sure there are any. You know, there's a bunch of things that allow you to mutate the vector, but there's not really much. Oh, there we go. As slice. Well, yeah, that probably isn't. That probably doesn't count, does it? I wanted to do it so I could call as slice. No, that doesn't make any sense.
Did you just control F X so?
I could. I'm just kind of, like I say, maybe I can. Maybe it'll be faster. I don't know if it'll be faster. There's capacity, but that's boring, right, normally. Maybe I do want to find out the capacity of this vector, and so I need the address of a vector, but that would be
work on a
really
slice too. I mean, isn't that provided for slices as well?
I don't think so, because slices don't really have a capacity, right? This isn't the length,
Oh, they
this
have
isn't
length,
their
yeah.
size, this is how many elements have you allocated storage to hold right now,
Oh.
which is not normally a thing anyone ever cares about. You can ask, as slice, len, yeah, boring, is empty, boring, those are both on slices as well. And then now we're down into methods from deref. So yeah, we absolutely are, no, there's absolutely no reason not to do this thing. In current standard library. Yeah, maybe you're supporting some future standard library now, but just take this. And just don't take, don't take some very specific type like U8, it's super magic, right? Do we even know at this point that those things were U8s? Yeah, we do. The type inferencer said, oh, well, you're making a vec of U8s, but so that 0.100 must be U8s, so that slice must be a slice of U8s. It figures all that out, right? But, what if I change that to be a vec of U16s? What would happen now? Nothing, right? Code would still work fine, right? Because I fixed that. And so now I have the freedom to go up and change the declaration of V and instantly get the right answer for a different source type. Make sense? Well, like I say, I didn't really mean to spend half an hour on that, but it seems like it might have been a useful half hour, so there we go. What is this? I don't even remember. I remember I had a link down here. Oh, reorder iterator. Oh, yeah, I want to show you that. I have no idea why that link is even right there. And the vec and array and slice methods are pretty cool. You can do some things on a vec or array that are pretty neat. You can use the vec as a good stack. So Rust doesn't have a built-in stack type in its standard library. It's just like we already set up a vec to work as that. So use a vec. And if you ever find yourself sort of taking elements from the front of a vector, you know you're doing it wrong. The stacks grow from the end, and push and pop work on the end of a stack. There's a retain method, which retains only certain methods of the vector. There's a dedupe method that keeps only certain elements of a vector. Keeps only non-matching elements of the vector. And Hook shows a trick of how you go ahead and use dedupe to dedupe a non-sorted vector. Split and join on slices is used a lot. Join in particular is used on string slices really, really commonly to join two strings containing words, or a slice containing a bunch of words. You join it on the space string and it now produces the words separated by a space. That's always really useful. Split is used a lot because borrow checker in particular, it's really common to split a mutable slice into pieces. Why? What's the advantage of splitting a mutable slice with split over taking a bunch of subslices of that mutable slice?
I wonder if that's the Rust compiler.
Yeah, that's the Rust compiler. Going, you guys are supposed to know this one. Okay, let's see what's going on here. Let me ask the question in the form of a code. Let's make a mutable slice. I don't know why I didn't do this some more principled way, but I didn't. Okay, here's a mutable slice with 4 numbers in it. Everybody agree?
Mm-hmm.
All right, well, let's take some pieces out of that slice. Heck, we don't need to make them mutable. Let's just take some pieces out of this slice. Sorry, I probably can't type today, my bad. So we'll take the first couple elements. We'll take the second couple of elements. And, oh, sorry, this should be 2 dot dot. So, and let's print these things, because that's always what you do with things in toy programs in the playground, is you print them. What else could you do with them? Yeah?
You're missing a space.
Yeah.
I'm sure I'm missing a space.
S back.
I have too many parentheses right there. What else?
One line
Um,
up. One line up on S back.
Yeah.
Oh, I see what you're saying. Yeah. All right. Everybody cool with that? Should anybody be cool with that?
Isn't it borrowing a mutable slice more than once?
Oh. Borrow checker doesn't like us very much now, right? What is the borrow checker afraid of here? What's its concern?
Multiple mutable references to the same thing.
Yeah, right? So I can now store through S front and S changes. I can store through S and S front changes, right? Or maybe S back changes, or maybe both. I don't know, right? Could those slices have been overlapping? Oh, yes, of course they could have, right? The borrow checker doesn't really keep track of that sort of thing. So this code's just not going to compile, because, that's no good. Let's try running it and see the borrow checker just completely freak out at us. Yep, cannot borrow more than once at a time. I guess it doesn't freak out at us, it just stops at the first place where you did the thing. Right, it won't even let the first one go through. The second one certainly is not okay.
Mm-hmm.
Well, let's see if we can get the borrow checker to love us here. It's always good to do that. So, standard slice split hat. Hopefully we'll figure out any Rust. The split struct, created by the split method on slices, returns an iterator over subslices that, so the split method actually contains, it lets me iterate over the things. There's also a split app method somewhere on slices that lets you actually split a slice into pieces, and treat the pieces as 2 mutable references. It consumes the thing so that the original can't conflict anymore. But that way you can get mutable references to the front half of the vector and the back half of the vector, which is nice, or the array or whatever. Which is nice, right? Because the borrow checker knows, because split app promised with unsafe code. Split app promises that those won't overlap. right? And so borrow checker's like, okay, I guess you got back to a non-overlapping mutable references, whatever, sounds good to me. Yeah.
And I just give that an example of some of the stuff you can do and why you should think about the borrow checker all the time. There's straightforward sorting. There's a binary search predicate. I don't want to tell you how many bugs I've found in people's binary searches over the years, but it's a very, very large number. It's really nice that the standard library has a bulletproof binary search on vectors and slices that you can just, tell it what you're looking for. It will actually, on an ordered, on a slice whose elements implement ORD, it will binary search it as though it were sorted, and then it will give you back an answer if there is one. It gives back an option, right? Which is exactly what you want it to give back. Oh, and another thing that's nice that Rust and Python do, but most other languages don't because they're frustrating. I guess that's what it is. Is if the elements are ordered, the arrays are ordered too. They're ordered lexicographically, right? They're ordered by elements front to back in the vector, and ties are broken by length, right? Shortest first. So it's absolutely standard lexicographic order. So I can compare two vectors if their elements are ordered to see which one's less than the other one. That's kind of neat. And can be really handy in some kinds of algorithms.
Do they have to be the same size?
They have to be the same type. I mean, size isn't good enough, right? They both have to implement, well, they both, sorry, that isn't even, I think, true, but there has to be an ORD implementation. Yeah, so they do have to be the same type, right? Both vectors have to be the same type because it's going to call the ORD implementation to compare them. I guess all that has to happen, I'm trying to remember how the order trait works. I guess all the thing that has to happen is that you have to be able to order the elements with each other. Let's see how the order trait works. I don't even remember anymore. Rust, std, ord. Does ord take two types or one type? I don't remember. Where's the trait declaration? Why do they always hide the trait declaration by default? That's super annoying. Oh no, it does take a right-hand side type. So yeah, they could be of different types as long as the thing on the left is ORed with respect to the thing on the right, we're good to go. Trait system's helping us here, right? It's making everything pretty and nice. But you can't just compare arbitrary types. They have to be orderable, because otherwise how would you compare them? Right. So, now sometimes a stack isn't enough. Sometimes you need a queue. You need to be able to put elements in at, stack is last in, first out, right? We want sometimes the first in, first out data structure, the queue, where you put things in and then they come out in the order they were put in. For Rust, the standard library provides a very, very nice type called vecdq, a very, very nice struct vecdq that actually is a circular queue stored in a vec. So it's very, very efficient and very, very easy to use, and it's basically always what you want for queues and stuff. There's also a linked list. I'm not going to show you my code from Plan B, but I have a bunch of code in my EVE Online route finder that actually uses a vecdq for searching things. Linked list is a doubly linked list. I've already mentioned many times learning Rust with entirely too many linked lists. If you read that book, you end up with an implementation that looks very much like what's in the standard collections for legacy reasons. A bunch of people have tried to get this thing dropped from the standard collections, but there you are, it's still there. Enough people wanted it. Just don't use it. It's pretty error prone. Its memory performance is terrible. Its API, last I checked, which was a long time ago, because OOG doesn't have so many of the things you want, in particular, if I remember right, there's no way to delete from an arbitrary place in a linked list, a Rust linked list. It's like, what? So yeah, that. Just don't use that. That one's a trap. My wife and I watch food programs a lot, cooking contest programs a lot. And, if you watch Chopped, there's a lot of sort of things like truffle oil. They always have it on the shelf, right? And if you ever see somebody use it, you're just like, no, it's a trap! Because, anybody who uses it just gets berated by the judges for using truffle oil. You're not actually supposed to use it, but they put it there anyway. Linked lists are like that. So, yeah, Rust list class. There's a binary heap. It's a max heap. You don't get a min heap. If you want a min heap, you can use the standard comp reverse type to turn it into a min heap, or you can play the usual games where you do something like negate the keys. Negate the elements. It's not a keyed heap, so the only operations available on it are sort of insert and extract, right? But having said that, it's a perfectly reasonable binary heap priority here, and is reasonably efficient. There's a thing called min-max heap on crates.io, which implements a heap that it supports insert, extract min, and extract max operations. It's perfectly reasonable, but it's still not a key heap. There's really no general key heap out there, and that I've seen, and so that's a problem. But most of the time, you don't need most of the and for that, it's really nice. You do something like A star search with that, perfectly reasonable. And then there's the elephant in the room. There's the one we actually care about. How is it 50 minutes gone already? Which is the hash map, the hash set, the B-tree map, the B-tree set. So, the first thing I should say is that I'm not going to talk much about the sets. So what's a map in Python, let's say? What is a map?
Dictionary.
It's a dictionary. What is a dictionary then?
A key value lookup.
Key value store, right? I can store things by key, values by key, and I can later extract the value associated with a given key, yeah? Yeah, Rust has those. They're called hash map and B-tree map in the standard library. They're two different collections. The only difference is that the hash variants are actually hash tables. They have the feature of constant time access with many air quotes around what constant time means in this context. But the point is it's pretty fast access. One of the things that happened in the last couple months is that the whole Rust hash table implementation was completely replaced by one from a crate that had formerly been external to improve the performance, which is interesting, right? I mean, this code started out in somebody else's crate. Eventually, everybody in Rust is like, why don't we just make this the standard one? It works better. It's like, okay, so that happened. And that's what people normally use. Most types in Rust implement the hash trait. Implementing the hash trait is what allows you to, store a thing use a thing as a key in the dictionary, and so hash map. There's also B-tree maps, which are a little more efficient of storage, definitely have better memory locality, which is really important on modern computers, but of course aren't constant time, they're log time for some log with some ridiculous space. So if you have way many elements, you might have more tree traversal steps in a B-tree map. Also, instead of requiring that the keys be hashable, they require that the keys be ordered, because that's how a B-tree works, so things have to obey the order properly. And people don't use them, I think, as often as they probably should sometimes, but that's, the default for most people is to use hash maps, not B-tree maps. Oh, the other thing that's nice about the B-tree maps is the B-tree maps themselves are ORed, so I can make a B-tree map of B-tree maps. I can't make a hash map of hash maps because it turns out that hash tables are not hashable things. So if I want to nest, I kind of am stuck with B-tree. And you don't want to nest very often, but I can remember times when it came up. a thing to keep in mind for these maps is that ownership and mutability really matter here. There's no way to mutate the key in place. The whole reason that the map owns its keys is so that people won't mutate them in place, right? It's important to the consistency and correctness of the hash algorithm, hash table algorithm, right? That the hash map algorithm or the B-tree map algorithm, that the keys don't change under you while the thing is alive. And so it takes ownership of the keys. It's like, no, you can't have those anymore, that's mine. So keep that in mind. There's a cool interface called the entry interface, which gets you, avoids extra lookups. So there's this common problem, right, in hash table usage and dictionary usage, where it's like, well, I want to increment the count of something in the dictionary. So I first check to see if it's in the dictionary, and then if it's not in the dictionary, I insert a 1 in there, and then otherwise I get what's in there out of the dictionary, I add 1 to it, I store it back into the dictionary. That's a lot of dictionary operations, right, just to increment a stupid counter. And so what the entry interface does, and Python has a similar thing even, is to let you sort of bypass all that and do one operation. Let me show you a little example of that actually running in practice. I'm going to increase this font size. I can't read it, the size it is. So this is a thing that makes histograms of things. I don't even remember what it makes histograms of anymore. Oh, I see. It just makes histograms of some dumb toy things. It can make a histogram of words in the Gettysburg Address, it looks like. So it's making char histograms, or it's making word